Math 1314, Tyler Junior College, Section 2.2, More on Functions and Their Graphs. Test for Symmetry, Examples. In the previous video, we defined what we meant by y-axis symmetry, x-axis symmetry, and origin symmetry for graphs, specifically for graphs of equations. Y-axis meaning that the left was the mirror image of the right, x-axis meaning the top was a mirror image of the bottom, and origin symmetry meaning that we could turn the graph upside down, or equivalently, if we took the right side of the graph and rotated it 180 degrees, we would get the left side of the graph. But I'd like to actually test some equations graphs for x-axis, y-axis, and origin symmetries. So we're going to do these three examples. A, y equals x to the third power minus 5x. B, 4x plus 9y equals 36. And C, 4x squared plus 9y squared equals 36. So let's start with A. And if you'll notice, I've summarized the test for y-axis, x-axis, and origin symmetry with what you replace with its negative. For y-axis, replace x with its negative. For x-axis, replace y with its negative. And for origin, you replace both of them. So we're almost going to make a 3x3 grid up here. Let's start with y-axis symmetry for the first equation. For y-axis symmetry, we replace the x with negative x. So let's take this equation, and everywhere there's an x, let's remove it and leave some empty parentheses, and then replace it with negative x. And now we need to clean it up and see if we preserved the original equation. This is really just a matter of deciding what happens to the negative. I know I'm going to get an x cubed, but will it be positive or negative? Well, when you raise a negative to the third power, the first two negatives multiply to make positive, but the third one comes back in and keeps it negative. So a negative raised to the third power, and more generically, a negative raised to an odd power, preserves the negative. So it stays a negative x cubed. On the second half, we have negative 5 times negative x, which is positive 5x. So, did the equation get preserved? Is it the same as it was before? No. Not the original. So the answer to y-axis symmetry is a resounding no. Let's try x-axis symmetry. For x-axis symmetry, let's move it down a little bit. For x-axis symmetry, we have to replace the y with the negative y. So, let's take out the y, replace it with the parentheses, leave everything else alone, so x to the third power minus 5x, replace the y with a negative y, and then see what happens. Well, nothing happens because the y was the only thing on the left side, so now the only thing on the left side is negative y equals x cubed minus 5x. Is this the original equation? No, it's not. You can tell because the right side is the same as it used to be, but the left side isn't. And it was the same back up here, but the opposite. The left side was the same, but the right side is not. If one side is the same, but the other one isn't, it's over. So this is also a resounding no, because this is not the original equation. Now, if you're thinking, but could I move stuff around? And, well, sometimes you can. But again, if one half is correct and the other isn't, it's over. Because changing one will mess up the other. So this is not the original, and no, this does not have x-axis symmetry. And by the way, there is no guarantee that an equations graph has any symmetries. So it's possible for the answer to be no all the way down a column. Let's try origin symmetry. For origin symmetry, we replace both variables with their negatives. So we're going to replace the y, the x and x cubed, and the x and minus 5x. So we get negative y equals negative x cubed minus 5 times negative x. Now, we already know that nothing happened on the left. It stays a negative y. And we already know what happens when we plug in negatives on the right. We did it up here. We got negative x to the third plus 5x. Is this the original equation? Well, before you say no, the left side is not the same as it used to be, and the right side is not the same as it used to be. So we can't use the same criteria that we used up here, where one side was the same, but the other one was not. Here, it was the right side was the same, but the left was not. If one side matches and the other doesn't, there's no way you can restore it. But neither side matches originally. So sometimes, when you're not sure, you have to ask yourself, can I massage the equation and make it look like the original one? For example, can I make the left side of this look like it used to? Sure. How? What if I multiplied it by -1? If I multiplied negative y by -1, it would turn into positive y. So to see if this restores it to the original equation, restore one side and see if the other side gets restored as well. So let's multiply both sides of this equation by -1. Why? Because that will restore the left side of the equation. But what will it do to the right side? Multiplying the left side by -1 gives us a positive y back, so there's the left side of the original. And on the right side, distributing the -1 will change everybody's sign. So the negative x to the third becomes x to the third, the positive 5x becomes negative 5x, and lo and behold, that is the original equation. Again, the decision to multiply by -1 was motivated by the fact that neither the left nor the right matches the original, so I don't know if it is the original equation yet. Multiplying by -1 turned the left back to the original, and it turned the right back to the original. Why didn't I try it up here? Because one side already matched. If I tried it up here and multiplied by -1, it would fix this and mess that up. Same thing up here. So if both sides are wrong, maybe they're both wrong for the same reasons, and fixing one side fixes the other. Because this restores it back to the original, the answer to origin symmetry is yes. The rest of these will go a little quicker. Let's try B. 4x plus 9y equals 36. For y-axis symmetry, we just replace x with -x. I'm going to stop switching markers for the sake of time. If we replace the x with the -x, we get 4 times -x plus 9y equals 36. 4 times -x is -4x plus 9y equals 36. And now let's examine both sides. Is the left side original? No. Don't shut it down yet. Is the right side original? Yes. So anything I do to fix the left side would mess up the left side. There's no way to restore this. This is a resounding no. Let's try the X-axis symmetry, where we replace the y with a -y. So 4x plus 9 times parentheses -y equals 36. The 4x stays the same, but 9 times -y is -9y. That's equal to 36. Is the left side original? No. Don't make a decision yet. Is the right side original? Yes. Since the right side is correct, but the left side is wrong, anything I do to fix the left side, well, how could I fix the left side? Multiply by -1? That would fix the y and mess up the x. This is not the original equation. This does not have X-axis symmetry. And what about origin symmetry? Well, we change both of them. So 4 times -x plus 9 times -y equals 36. Now we get -4x and -9y equals 36, and we're in the exact same dilemma. The right side's not changing. The right side's always 36. So if the left side doesn't go back to being original, it's over. This one does not have origin symmetry. In the back of my mind, I'm thinking if one side's original and the other one's not, it's over. I know examples where that's not the case, because you can change one side of an equation without affecting the other, but it usually involves fractions, which we don't have here. So no symmetries here. What about this guy? Well, let's think about it before we do anything. We know what happens when you raise a negative to an odd power. The negative stays behind. Because if you have an odd number of negatives, all of them pair off to make positives except one, and that one negative keeps it negative. But what happens when you raise a negative to an even power? Like if you raised a negative to the 4th power, 2 of the negatives pair off and make a positive, 2 of the negatives pair off and make a positive, all the negatives pair off and make the positives, no negatives left, and it turns out positive. So without even substituting anything, I know putting a negative here is going to make the negative vanish. And the same thing here. So I'm expecting this to be yes, yes, yes. Y-axis symmetry. Substitute negative x for the x, except now it's getting squared. Plus 9y squared equals 36. The square kills the negative. We have 4x squared plus 9y squared equals 36. That is exactly the original equation. So this is a yes. And I think for the sake of time, I can go ahead and tell you that all of these are going to be yes. So now we went from having no symmetries to having all of them. Well, good grief, how can a graph have all three symmetries? And what does this graph look like? Well, I'll show you what it looks like. This graph, if you go left and right 3, and up and down 2, you get what's called an ellipse. It's like a circle, except it's more like an oval. So this graph has y-axis symmetry, x-axis symmetry, and origin symmetry. But it's not a function. It's okay, we're talking equations. What about functions? Wait a second, before I stop this video. We've talked about equations, but we're really talking about functions. So it's a natural question to ask, can we do this for functions and not equations? Yes. One way is just replacing f of x with y, but can't we do that without it? We can and we will.